This one is about a diamond. White light, which is a combination of all the colors, as you probably know, is incident on the surface of a diamond at an angle of incidence theta A for some reason. And they point out that a diamond is pretty and colorful because the index is very large compared to glass, but it also changes with color, with wavelength. So they give you the index for red is 2.41, the index for blue is 2.45. I'll tell you a little secret. Silicon carbide actually has a higher index than that, and it's a lot cheaper. So if you're buying a ring, you could probably get away with silicon carbide, but you didn't hear that from me. Okay, so it goes on to say, it also points out they're sometimes pretty because what will happen is you'll have total internal reflection maybe of the blue and not the red, depending on the angles that everything comes in. So the first question is about total internal reflection. They say, what is theta critical for the blue light? Is the question. What is the critical angle, which is the angle at which it changes from some of the light refracting out to total internal reflection? So it's a simple formula. Let's talk about it for a second, just in case you don't remember the simple formula when you're on the exam. Remember that total internal reflection occurs when, remember, as this angle gets bigger, the refracted angle, remember the refracted light falls away from the normal when you go from a high index to a low index, and eventually it'll fall away so hard it will refract out at 90 degrees. And if you go any further, it has nowhere else to go. It all stays in the material. So if you forget the formula, just remember it happens when theta transmitted is 90 degrees. And then you just set up a Snell's law. You say I come in at the critical angle in the high index, so for blue, 2.45, at the critical angle that I'm looking for, that would go into air, in this case, 1 times the sine, and it happens when you hit 90 degrees on the transmitted angle, so sine of 90, which is just 1. So what this shows you, 1 times 1 is 1. The formula then you remember. The formula is that the sine of the critical angle equals 1 over the index you're coming out of. Right, so sine theta c is 1 over 2.45. So that value, once you run the numbers, is 24.1 degrees. And that's the answer to part A. Part B. Part B tells you that it was cut at this angle here. That's an important angle in diamonds and jewelry making, I suppose. And they call that alpha. That angle is alpha. So the question is, so they tell you that alpha is 45 degrees. So find largest theta A, so that blue light is total goes through total internal reflection. Largest theta A, so that blue goes through total internal reflection. All right. So we know that we get total internal reflection of blue if the theta incident is greater than 24.1 degrees. That's what we decided last time. So I'm going to start drawing some new angles on here we're going to have to think about. We're going to say that's still theta A. We're going to call theta incident right here. We called it the critical angle before, but now I'm going to call it theta incident. And we're going to have to involve this angle, the angle that the theta blue transmitted into first. So I'm going to call that theta t. So don't mix up. We're not going to do Snell's law between this theta I and this theta t. Okay, they're separate in this case. Let's see. So now we have to do geometry, not physics, right? So I'm going to redraw this corner and show you how to figure out the geometry, because basically we're assuming it's greater than, but we're really saying when this is at the critical angle, what is theta A? That's really the question. Bigger than, smaller than, don't worry about that. It's just when we're at the critical angle, what's theta A? That's going to be the answer. So let me draw this thing again here, but bigger. right? So there's alpha. And our problem is we have a normal here, like that. And we have light coming down like that, right? And then we have a normal here. And then the light bounces. So here is theta t, and here is theta I. And we have to find theta A. And that's what we're working on. So you can probably tell we really just need to find theta t and then use Snell's law to get theta A. That's the strategy. But the question is, if we know this angle, how do we find that angle? There's a lot of triangles flying around on this thing. So I would say my tips here, if you're in a situation like this, one, is extend the normals. Usually you just draw the normal enough to kind of see how your rays are going to move. But here we need to draw them all the way across because we're going to need to make some triangles out of them. Right? So there's a normal. And there's a normal. That might help. And then, two, is find right triangles. Because what we're trying to do now is find the relationship between these two angles. We have this one, we want that one. We have a lot of triangles everywhere. There's probably 100 ways to do this. Right? So I'm just going to show you the way I did it, if I can remember. Let's see, the next thing is to remember that normals are normal. They are at right angles to the surface. So I found a right triangle here. I drew this 90-degree angle right there and said, okay, if that is 90 degrees, then there's a triangle right there, a 90-degree triangle. That's 90. This and this must add up to 90. So I'm not using theta I there. I'm just using the normal, because it's 90 degrees, it hits that side, and we know that's alpha. So this angle is 90 minus alpha, right there. Because the whole triangle has to add up to 180, so 90 plus these two together make 90. So that's 90 minus alpha. And then the next one I used was right here. That's 90 degrees, so there's a triangle. And if that's 90, and then these two together must make 90, but if that's 90 minus alpha, oh, this must be alpha. Right. So if that's alpha, then what is this one? Those two together have to add up to be 180. I completely lost track. So we'll call this one with my 4 bars theta x. It's the angle we had to use to get there. Right? So theta x is 180 minus alpha. Okay. And I know that because they add up to a straight line. Right? So it's 180. Okay, so now we have a triangle right here, the main triangle with theta I and theta t in it, and we know the third angle of that triangle now. And the angles of any 3 triangles add up to 180. It's not just for right triangles, it's for any triangle. So we can say that 180 equals theta t plus theta I plus 180 minus alpha. And then the 180s go away, the alpha comes over here, and you see that it's just the case that alpha equals theta t plus theta I. That comes out so sort of simple, there has to be an easier way to get there with geometry. I'm not sure what it is. That's how I got there. So we know that alpha is 45, and we know theta I is 24 by 1, so then we get that theta t is 45 minus 24.1. So we know that it's 20.9 degrees. So now we know theta t. So now we get theta A from Snell's law. 1 times the sine of theta A, because it's an air, equals 2.45 times the sine of 20.9 degrees. And blah, 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 blah. Theta A is 60.9 degrees.